moles. Okay, so the way that I think about a mole of something is, you know how we use the word dozen to describe 12? So you think of a dozen eggs, you know, oh, that means there's 12 eggs, right? And so moles just basically means that there is 6.022 times 10 to the 23rd parts. Or you can think of that as atoms, molecules, whatever, however you want to, however the question is asking. But that's how many pieces to that one big group. And so when you think of mole, 1 mole is equal to this. 1 mole equals that many pieces. And this number right here is, like you said, Avogadro's number. And so, yeah, this just kind of helps us organize, because, you know, in one small sample, 1 gram of a substance, you know, there's tons and tons of atoms. And so that's why we use moles, is just to work with smaller numbers and things like that. Okay. And so we'd use Avogadro's number to get from grams to those actual number of particles. Does that make sense? Mm-hmm. Okay, so all of this is, I know it looks like it's a big number and there's a lot of numbers involved, but in the end, it makes a lot of the conversions and calculations a lot simpler when we use moles or whatever, just so it makes the numbers smaller for us. So for example, we would, on the periodic table, the atomic weight that you see on the periodic table is how many grams per 1 mole a substance weighs. And so for that example that you had right here for iron, 1 mole of iron is equal to 55.85 grams. So iron is Fe, so 55.85, right?
Yeah, right.
85 grams, and that's per mole. So for every mole of iron that you have, you'll have 55.85 grams.
Okay.
That's how much it will be.
Okay.
Does that make sense?
Mm-hmm.
Did you have a different question?
No, that makes sense.
Okay. And so looking at this right here, this is going to help us understand how to get to the actual pieces of how many atoms are in this much iron. And so the way that we would set this up is just using a conversion chart. And so we'd start with 55.85 grams. This is how I set up all my conversion charts. It looks kind of like a T, you know, just intersecting all the time. And so this is grams per mole. So the moles go on the bottom. And so we want to get from grams per mole, and we want to see how many atoms are in, we want to convert this many grams into moles or whatever. Does that make any sense? And so we'll end up just getting Avogadro's number if we use this, so we'll use a different number for that. So basically, and this will be more common questions that you'll see in the future, is going from grams to however many atoms there are in that substance. So this is its molecular weight that we have for iron. So let's say we have 25 grams of iron, and we want to see how many moles we have of iron. Does that make sense? So we want to get from grams to moles of iron. And so we'd set up this chart and would have 25 grams of that iron, and then this is our conversion, right? So we want to go from grams to moles. So the grams would need to be on the bottom. You're exactly right. So 55.85 grams, and then that's per 1 mole. And then if we do the math on that one, we can figure out exactly how much 25 grams is of iron, how many moles of that is that there are.
Times it and divide it.
So yeah, we take 25 divided by 55.85. So let me do the math real quick. So that ends up equaling 0.44. Oh, and this is I'm glad that we brought this up. So kind of connecting back to significant figures. Whenever we use two different numbers.
Okay.
Mm-hmm. So this number right here at the bottom has more significant digits than the 25 does, right?
Mm-hmm.
And because we're doing multiplication and addition, multiplication and division have the same rule, and that is to go with the number that has the least number of significant digits, and that's what you should make your answer. And so, for example, when you type
At least, so just 2.
right, and so for this, if you put it on the calculator, it comes up with a gigantic decimal number.
Yeah.
And so you just want to round and make it just 2 significant digits after the decimal point, because we only have that 25 right here.
7?
So it's 0.47 instead of 0.446. It was.
Wouldn't you round up to 5?
Oh yeah, you're right. I was thinking of the. I was thinking of the other number behind it.
Yeah.
You're right. So it would be 5. Perfect. Mm-hmm. Yeah.
Nice. Okay. So at least.
And this is moles. And so those grams cancel, and so that's why our units are left with the moles.
Okay. And then since the significant figure, that makes it more precise.
So
more accurate.
So great. I'm glad that you brought that up. So this number is more precise because it has more significant digits.
Mm.
This number is a less precise number. And so when it comes to choosing the more precise or the less precise, we always have to go with the least amount of precision that we have. And so that's why we choose 2.
That's weird.
That's why we choose, because we don't know how far this number is significant after. We don't have, our certainty level is just to the ones place. And this certainty level is all the way out to the hundredths place. And so if you think about it, if we were adding these 2 numbers together, we would keep this last little bit, right? Because we're adding 2 sums.
Right.
But because there's a level of uncertainty here when we're doing the multiplication and division, we have to go with the least amount of significant digits. So that's why this answer ends up just being 0.45.
Okay. That works.
Yeah, that was good. Good. I'm glad that we saw an example of that because that's important. And then what we use from this point, if we want to get to the amount of atoms, we would then take, I'm going to erase this top part.
Okay.
We would then take that 0.45 moles.
And do the big number.
Exactly right. And so 1 mole has
6 on top. The
Yeah.
big avocado.
exactly Avogadro's number. Atoms. Perfect.
And 45 would be that empty box would be atoms, or 1.
This right here we wouldn't have anything
Nothing.
because it's not moles per something, it's just moles. Right, so there's no fraction. And so these moles cancel, right?
Right.
And so the units that we would be left with is atoms.
That's
And
okay.
then, and then if we just do the math, it would be 0.45 times Avogadro's number.
All of my quizzes I mixed up are my thing.
Oh,
And then-
which goes on the top and the bottom?
Yeah, and he's like, he wrote me a little note saying, always label your stuff,
Mhm.
so you know what cancels with what, and you see what you're left with.
Exactly.
Yeah.
And
Okay.
and when you get the hang of what units are what and all the prefixes and everything, I remember there was some problems in chemistry that I couldn't remember what to do, but I knew what units the answer were in,
Mm-hmm.
and so I was like, okay, well, it has to have these units, and so I could manipulate the formula to make the units cancel out with the numbers that I was using, so that way I got the math right, even though I didn't really know what it was. So it's kind of like a cheat almost.
Yeah.
And so if you know, so if you know the units for the answer, then you know what needs to cancel, and that's how you can figure out what goes on the top and the bottom. Perfect.
We just multiply that straight across.
Right, just straight across, and then we get our answer. And my cell phone calculator, I don't think we'll do that
Yeah,
big
yeah,
number. So
That's
yeah,
good. Jeez.
perfect.
Nice, that works.